Hi class, my name is Elizabeth Talbert and my presentation will be on digital microfluidic logic gates and their application in built-in self-test of lab-on-a-chip. So first, what is a microfluidic chip? So a microfluidic chip, it's a little chip that has channels etched or molded into it. So these channels operate on the micro scale, so volumes of microliters or even sometimes nanoliters of fluid are passed through the channels of this chip. And different laboratory procedures can be conducted within these channels. So here, that would be the body of the microfluidic chip. And applications of this chip can range from clinical diagnostics, DNA sequencing, toxicity testing, just to name a few. So these are largely biomedical applications, but other laboratory procedures can also be processed in a microfluidic chip. And since the volume of fluids that are ran through these microfluidic chips are very small, so for example, maybe the droplet that you want to conduct testing on is only 1 microliter. If there's any variation in this volume, then the test results could be incorrect, given that maybe it's smaller. So the droplet that's actually run is 0.8 microliters. This droplet would yield an incorrect test result because it's the wrong volume. Even though the difference in the volume, 1 microliter to 0.8 microliters, is very small. And these differences in volumes can affect the validity of the test results taken from the microfluidic chip. So in the paper that I'm discussing, Zhao and Chakravarti they create a mechanism to test if these volumes are correct, and they do that using microfluidic logic gates. So what we've discussed in class are digital logic gates that utilize electric signals to determine logic values. So a high voltage signal will be given a logic value of 1 and a low voltage signal will be given a logic value of 0. When the logic gate is applied to a microfluidic channel, you sketch out a channel. Here are the inputs, and this is an output. So a logic value, let's say here's a droplet of the appropriate volume, let's just call it 1x, and a volume of 1x or greater will be given a logic value of 1. A volume of 1x or smaller, a volume of smaller than 1x will be given a logic value of 0. So if you have two droplets, both of 1x, so this is a 1 and a 1, maybe this is an OR gate, you'll yield an output of 1 or logic value of 1. So how do these actually work? How do you make microfluidic channels into a logic gate? So here are two examples of an OR gate. On the left, we have the inputs 1, 1. On the right, we have the inputs 1, 0. So I'll discuss the left first. Here are the inputs. This is where the output will be. This is a reference droplet. This is a waste reservoir. And this is a washing droplet that just clears the gate after it's used. So what happens is the inputs are first diverted into the processing channel. So this middle section of the microfluidic design is a processing channel. So the droplets are diverted into the processing channel, and the way that they are moved is through electrowetting on dielectric. And what that means is that there's little droplets that go through the channels of this microfluidic chip. That's a droplet, say that's the surface of the chip. And electric pulses are generated and directed to a certain spot of the channel surface, and that repels or attracts a droplet. So that causes the droplet movement. And these electric pulses are controlled using a clock. So back to the microfluidic channels. The droplets are diverted into, in this step, the droplets are diverted into the processing channel. Droplets are merged together, and then the droplets are split. And now in this step, the volume of the split droplets. In this case, they're both 1x. And for the next step, a volume of 1x is needed for only one of the droplets. So the second droplet, this one, is diverted into the waste reservoir because there only needs to be one droplet of a 1x volume in that channel at that time. So that one of those droplets is combined with a reference droplet. That reference droplet is diverted down the channel. It's split again in the next step, and one of those droplets is put into the output, yielding an output of 1. For the input 1, 0, a similar procedure occurs, except in this step where the droplets are split after they've been merged, there are two 0.5x volume droplets, and since there is no 1x droplet, or there aren't two 1x droplets present in the channel at this time, neither of them are diverted into the waste reservoir, so this remains empty. Similar to the previous example, a reference droplet is diverted through the channel. This time it combines with both this time it combines with both 0.5x droplets, and it yields, see it's diverted down, and that yields a droplet of 2x in its volume. That droplet is split, and the output again is 1. So this is an OR gate. An AND gate functions in a similar manner, where droplets are diverted, split, and merged to yield an appropriate output. For the sake of time, I won't go into too much detail on how this works, but there will be a link to the presentation which contains detailed notes. So here is the output, or input 1, 1, which yields 1, 1, 0 on the right, which yields 0. Same thing for the inverter. Here's the input. So input 1, it's a bad one. Input 1, output 0. Input 0, output 1. For the compressor, which is the built-in self-test and the main focus of this paper, these logic gates are utilized to test whether or not the volumes of the liquids were appropriate for testing in that particular microfluidic chip. So here we have a chip, and you may have input droplets of a certain volume. Tests or laboratory procedures are conducted on these droplets, and here are your results. So to test if these results are accurate, the droplets are diverted into what is called a compressor, and it is called a compressor because it takes all of the droplets and determines one logic value for all of those droplets. So here we use AND gates, and a logic value of 1 means that all of them are valid. A logic value of 0 means that at least one input was invalid, and here we could see it's that particular droplet. And you could trace back the origin by looking at the results through each level of the 3-level circuit. Here's the second compressor design. This one utilizes NOT and OR gates. Same idea, except a logic value of 0 means that there are no defects, and a logic value of 1 means that there was an invalid droplet somewhere. And this compressor also utilizes all of the droplets from the laboratory testing to yield one output. But in this compressor, the droplets are split first before they are processed, and then they are merged together. So split droplets are merged together. And then these merged droplets are processed through the circuit. And this is a 4-level circuit.